This lesson deals with a piece-by simulation of a step-down regulator and also the analysis of an inverting regulator. You can find these notes in the ECE402 ebook in Chapter 8 starting on page 19. What's shown here is an implementation of our step-down regulator using a 555 timer. There's a lot of ways of doing this. This is an old design, probably a lot simpler ways of doing this, but I like this particular implementation is because we have a model for the 555 timer. And we can kind of see how the control loop works and how we basically go to a value in steady state. Let me explain a little bit of how this circuit works, and then we'll take a look at the simulation. So here is our diode, inductor, capacitor, and here's our load. And this transistor here, this power transistor, is going to be our switch, and it's going to be controlled by the output of the timer. So when the output of the timer is high, this transistor saturates, and we pull current through here, and we close this switch. When the timer is off, this transistor is cut off, no base current flows, and so the switch is off. Now there's a control loop here. This comes back around here, and it comes back to a Zener diode, which has a Zener voltage of 8.2 volts. If this Zener is on, and we have current to forward bias this base emitter junction, so this node voltage would be roughly 8.2 plus 0.7 or 8.9. So if we neglect the value of the voltage across this resistor because the currents are kind of small, when this voltage gets to 8.9 volts, this transistor will saturate, and that'll pull this point low, and that's going to reset the timer, which means the output's going to go low. Here's a Zener diode over here to give us a nice crisp voltage for VCC. And of course we have our astable configuration here. The file is shown below. We're using an oscillator, so we want to have a pulsed input, so we're going to turn the power supply on with just a slight delay in our simulation. This is the article where I found the 555 timers. Let's take a look at some of the results. This first graph is node voltage 3. This is the output of the astable. Initially goes high, then goes low, and then becomes a series of short pulses. This voltage here is the voltage across the capacitor in the astable. You see it begins to charge up, and then just sort of RC decays, and then goes into what looks like a sawtooth pattern, which is not its normal behavior. Kind of see why this is happening by looking at the reset pin. Initially the reset pin is high, then all of a sudden it gets pulled low, basically shuts off the timer, and then this begins to RC decay because we're basically resetting everything. But eventually the reset pin goes into a series of pulses. We'll figure out why in a little bit. And lastly, this is the voltage across the capacitor and resistive load. Starts out at 0, actually shoots beyond its final value, which is around 8.9 volts. And then it comes back down and reaches some kind of a steady state with a ripple you can see in it. So what's going on? Well, initially when you first turn on the circuit, the capacitor is not charged, and that causes the output of the astable to go high. And when that goes high, the discharge transistor is cut off and the capacitor begins to charge. The reset pin is high because the transistor Q1 with the Zener diode doesn't have enough voltage at its input to saturate that transistor. We need to have an output voltage around 8.9 volts. But that's what happens over here. We eventually cross that value right about here, and all this stuff starts to happen. But there is a power diode in our regulator. It's called D1. It's an MBR 1035. It's a power diode, and it has a time delay. It can't switch instantaneously. So you're actually seeing a little bit of a time delay before that can kick in. When that happens, the transistor Q3 is cut off, and now our switch is open, and we begin to RC decay with the capacitor and resistive load. But eventually we come back down to this 8.9 volts roughly, and you can see that things begin to happen. And we've kind of reached some stuff in steady state. Let's also take a look at some of the currents in our circuit. Here's the inductor current. You can see initially it goes up quite high, and then begins to decrease, and eventually shut off, and then go into some kind of a pulse pattern again. Now, why this is happening on this positive slope here, the transistor Q3, which is a PNP, is actually saturated, so our switch is closed, and then it becomes open. And when it becomes open, then the diode D1 kicks in, jumps up, and then eventually the current goes to 0 in it. And this is the capacitor current. So we're charging the capacitor up, and the capacitor is discharging. Then eventually we get into a series of steady state pulses. Let's zoom in on these pulses and see what they look like. Here's the inductor current blown up. You can see that it's a triangle waveform. goes up to 347 milliamps. Again, this is after an initial charging cycle. And it comes back down to 0, and then starts up again, repeats itself. This is the current in the switch, which is the transistor Q3. Again, it's a PNP, so we're looking at the negative of the collector current. It's here it's on, then here it's off. And when that transistor switches off, the diode kicks in, jumps up to almost that same value, and then eventually goes back down to 0 as the inductor is discharging. And then here's the capacitor current. Goes up, starts out at minus 109 milliamps, then goes up to 237, comes back down again. Now, these pictures all look like the pictures we had on page 15 of the notes from our lecture last time. Next, I plotted the current in the resistor. Put it on kind of a large scale, so it appears to be a straight line. It has an average value of 109.5 milliamps, but there's a slight ripple in it. And so I took node voltage 11 and kind of zoomed on it. So you can see the ripple I've got here peak to peak. It's going between 8.838 volts and 8.6841. Let's compare some of these things with our formulas. So let me grab from our simulation. The value of ISO-P is 347 milliamps. The time t1 is 56 microseconds, and the period is 150 microseconds. My average current is 109.5 milliamps. The average output took the peak plus the minimum and then added those together and divided by 2, so I get 8.761. We were roughly guessing to be around 8.9 volts, so pretty close. And the ripple peak to peak is about 154 millivolts. Let's go back to our formulas. As I mentioned before, our formulas don't allow us to predict the results, but our controller has to allow these equations to be satisfied. Let's go take a look at some of these numbers. So our output average current was equal to this formula, 1/2 Vn over V0, T1 over T times ISO-P. So 1/2, 15 volt input, 8.761, my number I picked up over here, 56 microseconds divided by 150, and then times 347 milliamps. I get 110.9 milliamps. We measured 109.5, so pretty close. The output voltage is the square root of Vn ISO-P R sub L T1 over 2T. So 15 volts, 347 milliamps. I have an 80 ohm resistor for a load. 56 microseconds divided by 2 times 150. I get 8.816. I measure 8.761. Again, these formulas were derived assuming that we had a perfect diode, but I don't have a perfect diode. The ripple was this formula, 1 over 2C2. ISO-P minus I0 squared over ISO-P Vn over V0 times T1. So 1 over 250 microfarads, 347 milli minus 109.5 milli, quantity squared divided by 347 milli, times 15 divided by 8.761 times 56 microseconds, and I get 156 millivolts, measured 154. I'm next going to cut the load in half and see what happens. Before I do that, let me show you one more simulation that I didn't include in the notes, but I have emailed to you. And this is node voltage 10. This is the voltage across the diode, but from cathode to anode, so the negative of the voltage. You can see here there's a ringing that's here. This is actually sinusoidal in nature if you blow this up. And then you see a flat part here where the diode is actually off, and here's where the diode is on. And this is ringing or oscillating at about 262 kilohertz. I was kind of wondering, where's that coming from? Well, I have an inductor of 1 millihenry, and that inductor sees some capacitance looking back into the circuit. Now, at this frequency, the large capacitor we have for the load, the 50 microfarads, looks like a short circuit. But across the diode, when you reverse bias it with about 10 volts, you get about 250 picofarads of capacitance. There's also some base collector capacitance from our switching transistor, and that's on the order of about 160, 170 picofarads. So if you take 1 over square root of LC divided by 2 pi, to get this frequency with an inductor of 1 millihenry, you'd be looking at a capacitance that's on the order of 370 picofarads. So my guess is that's coming from the diode's capacitance and the base collector's capacitance. The problem with this kind of frequency is it generates noise and something that could be transmitted if you have any kind of wires in your circuit. One of the problems with switch mode power supplies is that they are a source of noise and interference. I also did one other plot, and this is the average voltage at node 10. So I used the average command and then went one period. It's the same value that we have across the load. And the reason for this is that the average voltage across the inductor is 0. just like the average current in a capacitor is 0. Let's go back and look at the notes again. So here I cut the resistor in half, and now my steady state results have changed. This interval of time is larger. It's almost a factor of 2. And this current is about a factor of 2. I mentioned that in our equation for the regulated voltage. Let me go back to the previous page. That if our controller keeps the output constant, and if our load were to change, say to be half as big, then this would have to be double in value. But if this is double in value, then this has to be double in value, and this would have to be double in value to cancel. That's exactly what happened. You can see likewise for the switch current coming up and going back down, the diode current, and then the capacitor current. So now my peak current is 357 milliamps. My time t1 is 104 microseconds, and the period is 264. Not exactly double, but it's close to that. And again, our formulas are just an approximation. Our next regulator is called an inverting regulator or a buck-boost converter. I forgot to explain where the word buck comes from. In our previous regulator, it was a step-down regulator, and our output was smaller than the input. So the output is bucking the input. Here, we're actually going to do something similar. We're going to take a voltage at the input. We're going to buck boost it. Buck is that we're going to make it smaller, but negative, in a sense, than boosting it in magnitude. Okay, how does this one work? What I've got here is an inductor, a diode and a capacitor, and a load, and a switch that's going to open and close, some type of controller. So let's assume that the switch closes, so the voltage across the inductor is in this direction, and the voltage here, let's assume it's initially 0. The voltage across the diode is 0 minus this voltage, so the diode would be off if we close the switch. So we've got Vn across it. Got the inductor and the battery hooked up. I get a voltage across the inductor, which is just equal to Vn, and the current's going to be the integral of that voltage divided by the inductance. So again, we're going to create a positive ramp of current. Now when the switch opens, the direction of current doesn't change, so the polarity across the inductor has to flip if we're going to be discharging. So in other words, we're now having current coming out of the plus terminal. That current is going to be pulled through the diode and through the capacitor. So we'll begin to charge the capacitor up where the ground is going to be positive and then this upper terminal will be negative. Eventually the inductor will discharge its energy. We'll close the switch again, force a voltage across here that's equal to Vn. But now the voltage across here is some positive value, or this node voltage is negative. This one minus this one would make the voltage across here strictly negative. Again, the diode's off. We charge up the inductor, open the switch, polarity flips, because we're now discharging the inductor. We're going to pull that current through the capacitor and through the load. So we'll eventually build up the load to some negative node voltage with some small ripple in it. This is all in words on this page here. Charge up the inductor, discharge it, and then eventually go to 0, and then we'll repeat the cycle again. So we come back over here, we have 0 current in the inductor in steady state. Now we close the switch. We begin to integrate that voltage. The switch is closed, so the current's going to follow the same pattern. At the same time, the diode is off. We're assuming that we've reached steady state, so there's a voltage across the load that's fairly constant with a little bit of ripple in it. Current on the average, again, this is shown in the opposite direction of our previous case because it's going to be a negative output voltage, is fairly constant. So I just call that capital I of 0 for its average value. And then what does the capacitor current look like? We have to go back and look at the schematic again. Let's do that on the previous page. The capacitor current is equal to this current plus this current. So I sub C1 is equal to I sub D1 minus I out. Go back to the previous page. It's my general expression at any instant in time. Now the diode current is 0 for this first interval when the switch is closed. So we just simply have the negative of I out. Let's calculate the current in the inductor. It's going to be 1 over L1. The integral of the voltage across is just going to be Vn. I'll do a d tau from 0 to t, so anywhere along that interval between 0 and t1, and with a 0 initial condition. So it's going to come out in front, be Vn over L1. This be the integral of 1 d tau, which is b tau, upper limit minus the lower limit. So this is my value of my ramp, And then when you get to time t1, that'll be our peak value of current like we did last time. Okay, now what happens? The switch opens and the coil begins to give up its energy. Now when the switch opens, there's no current in it. The current is being pulled through the diode, which is the same current as the inductor. Our output we're assuming is a constant voltage in steady state, so a constant current. And now we're simply going to subtract the diode current from the output current. Our current has jumped up to a value. Then we're going to subtract from that the value of I0. The maximum here is going to be I sub peak minus I0. And eventually the current in the coil goes to 0, and so the current in the diode also goes to 0. We just have simply minus I0. So our wave shape is a little bit different than last time. We've got this right triangle instead. Let's go back and see if we can calculate some of the currents in the circuit and some of the times. When this is discharging, what we've got is the voltage across the coil being integrated. What's the voltage across the coil? Let's just go back and look at the schematic. When the switch is open, the voltage across the coil is just this node voltage. Now again, it was defined with this polarity. So the rise in voltage would equal the drops around the loop. So the rise in voltage is equal to minus VD minus V out. That's my expression over here. But I do have an initial condition. That's my value of I sub peak, which is V in over L1 times T1. Yeah, let's assume that this voltage in magnitude is small enough that we could neglect it compared to V out. Just have minus V out here, so you can bring the minus sign out, bring the V out, take the integral of 1 d tau, and you just get the upper limit minus the lower limit, and then the value here at time t1 is our equation over here of V in over L1 times T1. That's our peak value. And now we can get an expression for the current in the inductor during this discharge cycle. And you can see here we've got a negative number. We're subtracting from that initial condition. So we are a ramp that's decreasing. Let's multiply this out. I got V out over L1 times T with a minus sign. And then I've got a plus sign here. So I got V out over L1 times T1. That's this expression. And I've got V in over L1 times T1. So put that in one term. And then if you wait to time T2, this current will eventually become 0 because I'm subtracting from this quantity. So let's find the time T2. So setting this equation equal to 0, I've got V0 over L1 with a minus sign times T2, and I've got this term over here. L1's cancel, divide those through by that. And this on the other side of the equation, then divide by V0, so I get V out plus V in over V0 times T1. Now in this particular case, I'm going to need to also have the expression for T2 minus T1. I want my calculation, so let's do that. So here's my expression for T2. Subtract T1 from it. My common denominator would be V0, so let's move V0 over V0. And this is going to cancel with this term, and I'm just left with V in over V0 times T1. Our average output current we're calling capital I sub capital 0. But because the capacitor current has an average current of 0, that just has to equal the average diode current, which we call capital I sub capital D1. What does a diode current look like? Well, it's a triangle wave. Let's go back to page 26. So we're looking at the area under the curve. It's going to be 1/2 the base times the height for the non-zero part here. So T2 minus T1, and then the height of I sub P. Use that to calculate the average value. So here's my 1/2 the base times the height, and then divide by the period. Bring out the 1/2. Now T2 minus T1 we found on the previous page to be V in over V0 times T1, and divide by T, and multiply by I sub P. So that's my value of I0. V out is R sub L times I out, so let's multiply this expression by R sub L. So I've got R sub L over 2, V in over V out, T1 over T, and then I sub P. Cross multiply here, I got a V0 squared. So then V0 is the square root of this quantity. This is exactly the same equation we had for the step-down regulator, but our output is actually a negative voltage as defined. Again, calculate the efficiency of our regulator. So we have that I out is 1/2 V in over V0 T1 over T times I sub P, but the power out is the voltage times the current. This would be our DC result. And this is going to be multiplying this by V0, which is going to get rid of the V0 term. So this is going to be my 1/2 V in T1 over T times I sub P. Now the power coming in is going to be the integral of the product of voltage and current divided by the period. But since V in is a constant, we can just simply pull that out. We simply have then just the average value of the current. So it's going to be V in times 1 over the period. And then let's take a look at the switch current on page 26. And my switch current, and it's a right triangle. It's 1/2 the base times the height, so that's 1/2 T1 times I sub P. Back to 27. So again, 1/2 the base times the height. We've got Vn, got the 1/2 T1 over T and I sub P. These are the same expressions, so again we have 100% efficiency. But in reality it won't be 100%, but a little bit less than that because we've neglected to drop across the diode. I haven't included any inductor losses or any switch losses, but again this is going to take us somewhere in the 90% range. On pages 17 and 18 we found the ripple by finding the peak-to-peak voltage across the capacitor when the current passing through it was 0. So we can use exactly the same technique again, where our capacitor current crosses 0 is between T3 and T1. We'll go back and look at this a little bit. So we have the same equation again. It's going to be 1 over C integral from T1 to T of the capacitor current. Go back and find the picture for the capacitor current back on page 26. So let's do that again. Here's T3 minus T1. Here's my height of I sub P minus I0. So it's going to be 1 over C1, 1/2 this difference times this minus 0. I don't have an expression for T3 minus T1, but I do for T2 minus T1. So again, I could use similar triangles. So the ratio of this height to this, so it'll be I sub P minus I0 minus a minus I0, which would be just I sub P divided by T2 minus T1. As a ratio, it has to be the same as the difference of this with 0, which would be I sub P minus I0 minus 0 divided by T3 minus T1. It's back on page 28. Our formula for similar triangles. So that's this expression right here. So I'm going to get rid of this T3 minus T1. So again, my ripple is going to be 1/2 C1. T3 minus T1 is going to be equal to, now if I just bring this over here, it's going to be I sub P minus I0 times T2 minus T1 divided by I sub P. And I'm going to multiply that by I sub P minus I0. We're going to get I sub P minus I0 times itself, so you get that squared divided by I sub P, and then T2 minus T1. We show that T2 minus T1 was Vn over V0 times T1. This is our expression for the ripple. This again won't help us solve for the ripple, but simply our controller has to let this happen. That if we make the capacitor bigger, we make the ripple smaller. It's actually the same formula we had for the step-down regulator, except that we're looking at a negative output voltage. And this was a piece-by simulation of our step-down regulator and an explanation of how the inverting regulator works.